G'day, this is Lee from Platypus Technical. Welcome to part 1 of our series about using a thermistor and a microbit to accurately measure temperature. So Platypus Technical is a science and engineering consultancy. We do research and development, but we also make resources to teach science and engineering to school students. So I want to know what you want to learn. Let me know in the comments or through Twitter, Facebook or Instagram, which is also linked below. So in December we did a series on the microbit advent calendar produced by Little Bird, and the feedback was that you wanted to know more about sensors and outputs and how to use them with a microbit. I want to go one step further and show you what you need to make accurate and precise measurements with those sensors, which will include explaining a little bit of the first principles. I'm hoping that this means you'll learn more about measurement and programming and electronics to allow you to make your own projects and build designs based on your own ideas rather than having to rely on kit projects. Now, I chose a thermistor because a thermistor is a simple device which makes it easy to use, but it also means that there are a few extra steps to get an accurate measurement out of it, which gives us the opportunity to explain some of the principles behind accurate and precise measurement. So as always, let me know your questions in the comments below or through the social media, and let's get on with it. So in this video we're going to focus on the thermistor itself. Thermistors are a passive electronic component, which means they don't do much if you don't put them in an electrical circuit. Really they just provide a resistance. So that means resistance to the electrons flowing through the circuit. So electrons go around an electrical circuit, and the higher the resistance in the circuit, the more voltage you need to apply to get the same electrons or the same number of electrons to move through the circuit. What's special about thermistors is their resistance changes depending upon the temperature. That means that we can use them as a transducer, which is a term used in measurement where we are converting one thing that we want to measure but can't do so directly with our device to something we can measure. So in the case of our microbit, we are going to use a thermistor to convert temperature into something that our microbit can measure directly. Transducers are very common when you're measuring things with computers, because really computers can't actually measure much on their own. So this particular thermistor will reduce its resistance as temperature goes up. Now we can demonstrate that by putting it in a breadboard, getting an ohm meter, connecting our ohm meter to our thermistor, and measuring the resistance. Now we see at this temperature that this thermistor has a resistance of about 1.2 kilo ohms or 1200 ohms. Ohms is the unit that we use to measure electrical resistance. Now if I warm up my fingers by putting them in some warm water, dry the water off, it doesn't affect our circuit, I can heat up our thermistor and we see the resistance going down. So the more I heat up the thermistor, the lower its resistance will get. And as I let go, it starts to cool down again and the resistance increases. Now, this itself isn't particularly useful either, because our microbit doesn't directly measure resistance. To do this, you need an ohm meter and something that will read the output of the ohm meter. So to make it useful for our microbit, we really need to put it in an electrical circuit and convert our temperature to voltage, which our microbit can measure. So let's have a look at how we might do that. So here is our thermistor. If we want to put it in an electrical circuit, the simplest thing to do is connect it to a battery. So we have the symbol for thermistor, symbol for battery. In this case, it would be a 3.3 volt battery. And we would measure with our microbit the voltage across the thermistor. This simple circuit won't actually do what we want. The reason is that the voltage from the battery is only across the thermistor. Now, batteries don't change their voltage, so it's going to be 3.3 volts across this thermistor no matter what the temperature. What will actually happen in this circuit is that the voltage will always be 3.3 volts and the current, or the number of electrons going through the thermistor, will change with temperature. That's not useful because a microbit isn't set up to directly measure current either. So this simple circuit won't work. However, all we need to do to make our measurement circuit is add a constant resistor in series with our thermistor. So we still have our battery, we still have our thermistor, but now we have a constant resistor here as well. Now this circuit is called a voltage divider because what it does is it divides the voltage applied to the circuit between the two resistances. If these two resistances are the same, each one gets half of the voltage. If they are different, so let's say the thermistor makes up 1/3 of the resistance and constant is 2/3 of the resistance, then the thermistor would also get 1/3 of the voltage and the constant resistor would get 2/3. Now, we're still going to measure voltage across our thermistor. However, now, because of this constant resistance, when we change the value of this resistor, our thermistor, its share of the total voltage will change. Because this resistance doesn't change and the thermistor does, as the temperature goes up, this resistance goes down, which means its share of the voltage goes down, and we should see less voltage, on the thermistor, and more voltage on our constant resistor. So really we could actually measure across either and get the same effect, a voltage that changes with temperature. So let's see how this works in practice. So here we still have our thermistor in a breadboard. We want to build the circuit that I drew. So we have a constant resistor here, which we put in series. We connect the battery across the circuit. So as it's set up now, current is going to come in here to the thermistor, flow through the thermistor into our constant resistor, and then back to the battery. This time we're measuring voltage. We start across our thermistor. So we set to volts this time and turn on our battery. So we have about 2.57 volts across our thermistor. I'm going to heat up my fingers again. Heat up our thermistor. We see the voltage going down. Now that's quite a small change in voltage, 0.04 volts, but that's enough to get a measurement. And we can adjust how much voltage in the next video when we choose which resistor to use. Now just to demonstrate that we could also measure across the other resistor and still see a change here. So we see that the resistor is much smaller than the thermistor because it gets a much smaller share of the voltage. But if I heat up my fingers again, and heat our thermistor, we see that the voltage across our constant resistor also changes. But you'll notice it's also going up instead of down. So, because the share of the voltage changes with a change in temperature, we can measure voltage across either resistor in our divider. The useful thing here is that if we want our voltage to go up with temperature, we can measure here, and if we want our voltage to go down with temperature going up, we can measure on our thermistor. And just to show you that no matter what we do to our thermistor, the voltage of the whole circuit doesn't change. We can measure from one end to the other. We have 3.3 volts, and again, if I heat up my fingers and heat the resistor, we'll see that the voltage on the battery doesn't change at all. So this is the end of our video for today. What we've learned is that we can put a thermistor in a circuit and use it to create a voltage that changes with temperature. That's useful to us in this case because microbits can measure voltage directly. So in our next videos, we're going to look at how we can set up a circuit like this to create a voltage that changes with temperature so that we can measure it with our microbit. Thank you, and as always, if you have questions or comments or other things you'd like to learn about, please let us know.